Yes. Good morning. Good morning. Once again, for the fourth time this semester, YouTube tells me I am live. And since it worked the last three times, there's a fairly decent chance that I am in fact live and not talking into an empty faceless void in my room. Welcome back to information security. Welcome back to the fourth and final of my lectures on information security. As announced last time, today we will be going through a grab bag of stuff you wanted to hear about. Yes, I am seeing thumbs ups. That is good. That means I am in fact live. That's excellent. So for the fourth time, you know this slide by now. You know this slide by now. Let's just skip those, and let's just jump straight into the first point that people asked about. So the first point people asked about was the thing that was on the news recently. Log4Shell. Every vulnerability must have a fancy name, but that doesn't tell us what it's about. Yeah, so generally speaking, if your security vulnerability shows up on the front page of the Washington Post as the most serious security breach ever, you've got a problem. The internet is on fire. Security nightmare. Excellent. This is fine. So what happened? That is what we're here to break down, right? I mean, news headlines are cool and all, but we're here to study information security, and we're here to take something away from this disaster. Let's have a look. So what is Log4j? Let's start with the basics. So Log4j is a logging framework. Now, logging is something we poked some fun at last time, but it is a crucial part of software development, especially in a professional environment. Why? Because if you've got a bug and the user is telling you, well, you've got a bug, but you have no idea of figuring out what your software did at the time, then, well, you're going to have trouble fixing your bug. So in practice, everything gets logged all the time because storage is cheap and, well, logging is easy. So you need professional frameworks for this stuff because printf isn't going to cut it. So Log4j is, well, I wanted to say like one of the, but probably the logging solution that is used in Java. It's the big one that everybody defaults to. For those of you not familiar with logging frameworks, just imagining it's printf, but like 5,000 different features. Some examples are on the slides. For example, different log levels. You can say, okay, this is a debug log, and this is an info log, and this is a fatal log, right? It's like different kinds of how important is this log, and then you can just flip a configuration switch and say, okay, I'm done debugging this application. From now forward, just print only warnings and above, and don't print debug anymore. And you don't need to constantly add and remove printfs as the less structured programmers among us are want to do, such as myself. Feature-rich log routing is what they call it on their website. Effectively, what that means is you can configure where your log is written to, right? So, for example, you start out by just logging to the console because you're developing, but then you could just have a different configuration file on the production server, and suddenly the log statements that used to log to your standard output now start logging to a file, like a rolling file where it just keeps creating new files and archiving old ones. Or you can just, for example, you pick up this fancy new Amazon Cloud Services logging server and now you want to use it, you can just switch a config and all your log statements suddenly log to this logging server instead of a local file instead. So like a lot of flexibility there, and you just write the log statements once and then you don't have to touch them again, and just configuration can just deal with where it actually goes. Actually really cool. Looks like this in code. Just logger info. And then you see these format string parameters. These curly braces are placeholders, same as printf, except, well, because we're not living in the 90s anymore, we don't specify the type of our parameters. Our parameters are just chorus to strings because that's what makes sense. Right, everybody uses it. This is one of the most widely used This is one of the most widely used open source products in the world, possibly more widely used than like OpenSSL. So it's a big one. Okay, next point for background. So the JNDI, everything must have an acronym, the Java Naming and Directory Interface. What is this? This is essentially a URL for Java objects. So a unified string, a unified way of identifying a Java object by a string. Why would I need this? Well, for example, let's say you have some SQL database or some directory service, and you want to load an object from this directory service and then work with it, right? For example, let's say you have user information and you want to load the information for a user identified by this unified resource locator from a directory service. And of course, you don't want to write your custom service code for, let's say, LDAP, because what happens if 5 years down the road you decide to switch from LDAP to, I don't know, DNS, because you're now storing your user data in DNS. That's maybe not the best example, but maybe let's say you're starting with SQL and then you're transitioning to LDAP, or any sort of like transition between storages. You don't want to have to write new code, at least that's the thought process. You don't want to rewrite your entire user fetching logic. Why would you? You can just change the URL to use a different directory service, and Java does the backend stuff for you. Really cool in theory. Yeah. What's an important caveat here? So there's a really important caveat here, right? Because we're saying it load objects. So when you're talking about Java, objects include code. This is like I would say, somewhat questionable design decision. I mean, I'm a security expert, I can't help myself. But yes, in Java speak, if you're talking about loading objects, that always includes, unless otherwise specified, also loading their object code. So methods, functions, right? That object is not only, like you might imagine, a safe object in JSON. It's not just a glorified dictionary. It's actually functionality behind that. The thought process being that, well, I mean, what if you change how your objects get converted to a string, for example, right? Like, what if your backend service is now adopted a new object type, but you don't want to recompile all your services because of that, right? You can kind of follow the thought process. You want to minimize disruption. You want to minimize how often you need to restart your services. You don't want to have to recompile all your services just because some backend class changed its functionality. So, well, let's just include the object's bytecode and just, well, execute the object's bytecode. It sounds really, like, if I say it like this, it sounds like a really obvious mistake, because, like, for the last lecture at least, I've been harping on about separation of, what did I call it? Instructions and data, I believe. This is not that. This is not separating instructions and data. This is just trusting that surely you won't ever load data from an untrusted source. There is a reason why deserialization vulnerabilities are one of the most popular classes of vulnerabilities in Java. Yeah, so objects include code, which means this JNDI is now a standardized way to dynamically load code at runtime. Well, that's not optimal, but it is what it is. Next point. So, variable substitution. Log4j, as mentioned, has lots of features which are really useful. And at one time, somebody thought, well, what if I want to maybe I've got like 10 application servers, and I want each of my application servers to log to my fancy new cloud services logging server. But at some point, right, I need to be able to identify which server my log originated on, right? I mean, I need to be able to figure out if it was at server 1 or server 2 that threw this error, so I could actually debug it. So Log4j also has a system called variable substitution, which, well, substitutes placeholders. Again, this allows you to specify these this substitution token in braces, and then it substitutes that brace substitution token when you send a log message. Straightforward, right? So the problem, of course, I mean, it's obviously not straightforward because we're talking about the security nightmare. The problem here is, of course, that this operates on the final log output. Now, I haven't quite been able to figure out why that is, I will admit. And I'm not sure I have a good explanation for this. Maybe somebody else can provide one, but I don't have one. Why would you make this run on the final log output? I don't know. Probably like I'm not saying it's nonsense. Like I want to be careful here. Like I'm sure there was like some design thought process here. Like this was a thing that like was created not in one big step. Like if I'm talking about it like this, like in retrospect, it seems obvious, right? It seems so obvious what I'm getting at. It seems so obvious that, oh, this is bad, right? We just talked about, oh, this is arbitrary code. This is gonna be bad. But like you have different people that build these different features, right? Like there's one person that's writing this substitution code, and this substitution code starts out by only substituting, for example, the current Java version. That's what the examples in the examples in the documentation are usually like, oh, I'm gonna put the current Java version, or I'm gonna put the current computer name in the log. And that seems benign, right? I mean, you could argue like, oh, well, the worst thing that's gonna happen is, well, an attacker is gonna print the current Java version to my log file. Well, what, like, it seems weird, right? But like it still seems weird to me as a security professional that you would do that even with like relatively benign substitution behavior. Like even with like, for example, only the Java version or the whatever, like Java specific stuff. Even there it feels weird. But if you think about it, like this double substitution behavior, you want to substitute something in this pattern that you see on the slides. This ends up being a mess no matter which way you approach it. Like if you approach it as you first substitute in this pattern and then you substitute in the string, like you first substitute the thing in braces and then you substitute the message, you end up with the problem that, well, what if your variable that you inserted suddenly ends up having a percentage sign in there, right? Like what if your system's name, your computer name has a percentage sign? Then suddenly by doing the reverse, by first substituting this brace token and then substituting the normal format string, you again end up with problems. Like I can kind of in my mind like reconstruct why somebody might have done this at one point and just said, well, it's safe because I can only substitute like these 5 things and whatever. And then of course at some point somebody else came along and thought, well, wouldn't it make sense if this brace substitution syntax could use JNDI? Like this was not the same person. That's like, in retrospect, if we're talking about this as one monolithic application, it's all obvious. Well, obviously this is a terrible idea. Like if you're doing it one step at a time across many years, across different developers, like with nobody really having a big picture of the whole thing because nobody can because of how humongous this software is, it seems like a little thing. Like, oh, I'm adding JNDI support to this feature. Useful, right? I'm adding JNDI support. Maybe we want that. Maybe we want to, I don't know. Maybe we want to look up what our logging server is supposed to be called. Like that's kind of like this is the example from the documentation, right? Logging context name. What if I want to look up the current identifier for my logging server? Because what if that changes, right? I don't want to hard code an identifier in my configuration file. I want to be able to just dynamically request what am I supposed to be called, and then I put that in the log. Simple, right? Like it kind of makes sense if you look at it like one step at a time. And that's how these vulnerabilities usually get created. Like you add one step at a time and each step seems benign. But if you put it all together, it seems obvious that this is a vulnerability. In retrospect, this seems obvious. Yeah, as somebody already points out in Q&A, why does it even expand strings already expanded? Because like one expansion, like the first expansion is being done in the function call. Like you have this log string, which has the placeholders for the actual parameters of the logging function. And then you have the separate thing, the separate pattern layout, which is specified in the configuration. So this is parameters that come from program logic, like your application. And this is parameters that come from the setup of the server, like the environment setup, for example, like if you want. Like for example, these parameters are going to be the same in every single time you run this application, right? Like this string, the result of this logging operation is going to look the same every time you run the program. And this could be different on every server you run it on. Like if you have 20 servers, right? Or like say two different companies run the same program. Then this could be different for every company, because every company might have a different way that their logging files are parsed or stored or whatever. Like this is customizable in configuration, and this is just quote unquote hard-coded layout. It's not a good justification, right? Like it's still a bug, but like a bug is like it's like bad design behavior, but like you can kind of see the logic here. Like it makes sense in a weird way to be able to like do these things. So it's like not like I'm always very, very reluctant to say, well, this is obviously incompetence, because it isn't. Like it's like maybe a bit short-sighted, like adding a powerful feature like JNDI to this. Like maybe the person adding it wasn't quite aware of what JNDI does, or like I mean, yeah, like the problem is that user input is expanded again if you log it. Like somebody just said this in Q&A. The problem is that user input is expanded again. Yes, but like you very quickly get into a very complicated problem if you want to like what do you want to substitute? Like, do you want to like maybe you want to have, I don't know, maybe you want to have placeholders in the log string. I'm not sure, but like it's actually fairly hard, I think, to be able to like figure out how to do this two-stage thing without one of the two stages being able to influence the other. I mean, the solution ended up being just disabling this JNDI brace notation. So like I don't think there's like a clean solution that like ends up without any possibility for conflicts between the two. Because like either you have this brace substitutor thing, but then what if the brace substitutor thing has a percentage thing? Or you have this percentage substitution, but then what if there's a brace in there? Now, of course, from a security point of view, the one where the user input gets to substitute is problematic. But like I'm not trying to justify it here. Like it's very much a matter of like, this is a terrible idea. This should not have happened. But like there has to be some logic behind how it happened. People aren't incompetent typically. Like very rarely are people incompetent. Like truly out of their depth, I'm just adding stuff, and that like doesn't get through code review. Like on a project of this size has code review on its contributions. Like an obvious flaw, an obvious oversight wouldn't get through code review. Like there has to be some combination of, well, either people didn't realize what JNDI does, or they didn't realize that the substitution behavior worked the way it did. Like some combination of these things had to have happened for this to have happened. Now, of course, like we've been talking about it for the entire thing. Yeah, like what happens if the log message contains substitution patterns? Putting it all together, yeah, we have this first log instruction, which inserts the HTTP method. Okay, HTTP method, that's fairly safe, hopefully. In this case, that's just get. Remote address, yeah, we can't really influence that. Oh, yeah, but it also inserts an HTTP header. Well, we can influence that, and then we just send this formatting token in the HTTP header, and this gets logged. And then what happens when variable substitution kicks in? Well, we have a JNDI instruction that tells us to load an object, and object means code, and code means bad. So we load this arbitrary object code from able.org, and then we execute whatever the toString function of that object is, and if the toString function takes over your computer, then well, that's by design. Yeah, that's the bug. Yeah, it feels obvious when you look at it like this. Like when you put it on a slide like this feels like the most obvious thing ever. But the thing is, in practice, these things are never obvious until they are. Like once these things are obvious, well, then you have a bug. Like there's always that one moment where you look at the bug and you go, well, this should have been obvious. But when you implement it, it isn't obvious. I don't really have a better explanation of it than that. It's like, when you're viewing each part separately, it kind of makes sense in a weird way. And only when you view the big picture and when you say, okay, I'm going to put these 3 specific things in order, then suddenly it feels like, oh, this is the most obvious vulnerability in the existence of vulnerabilities. Anyway, so yeah, this bug first cropped up in early December. Public awareness was mostly due to people abusing it in Minecraft at first, because Minecraft, of course, is written in Java. And, well, everything gets logged, which includes chat messages. So people were arbitrary code executioning in Minecraft by putting stuff in chat. And then people realized, wait, this isn't actually a bug in Minecraft, this is actually a bug in Log4j, and at that point people realized we are pretty screwed. Yeah. A few additional points maybe on why this is the security nightmare and the biggest vulnerability ever, because I don't think it's that overstated. The problem with this vulnerability, or the danger of this vulnerability, is that it travels in strings. And that means that it's actually like it's not an interactive thing. It's not a thing where like, oh, I just patched the front end, like any of the many like RDP exploits, right? It's like, oh, you just patch the front end and then you're fine. You just patch the exposed servers and then you're good. And then your 4-year-old server that's quarantined somewhere in the back can keep doing its thing. Because that's simply not the case here. Because this travels in strings. Like, for example, if an attacker tried to exploit my web server at the start of December, like this bug starts getting traction, and an evil person or a security researcher, I mean anybody, just sprays these tokens over the internet, trying to figure out what's gonna happen. Like, just post this to a bunch of websites, see who reacts. And like maybe the web servers were configured well. Like, you can see that, like, for this to have impact, you need to be able to connect to evil.org, or at least that's not entirely true, but okay, we can talk about that in a bit. But you need to be able to make internet connections, right? You need to be able to load object code from an attacker-controlled source. If your server cannot make an internet connection because of firewall rules, this is not it's still a flaw, but you can't exploit it this way. Because if the computer tries to load object code from evil.org, and the firewall just goes, wait, you're a web server, you're not supposed to be making outbound connections, it just blocks the connection. This is why we have firewall rules. Well, then this does nothing. But what happens if this string, I mean, it's maybe not as likely with a user agent, but imagine if this is like, for example, a name. This is like a last name field. And now this in the web server doesn't trigger exploitation, but over time it gets processed on the back end, right? It travels. So for example, the attacker places an order, like an order for 500 bottles of olive oil. Don't ask me why I made that example. This travels through the back end, and eventually at the end of the month, it all gets, like, all the orders get archived and get reported to a billing system in the back. You can see where I'm going. Like, at the end of December, or at the end of the quarter maybe, this entire batch of orders, including this innocent-looking JDNI string, ends up in a billing system, and this billing system starts slowly chugging through all of these orders and processing them into a billing database. And at some point, it encounters a user that it doesn't know. So it tries to match this user's identity against its existing database. It doesn't find it. What happens? Well, you trigger an extra branch, and the extra branch says, create this user. Like, create the necessary data to handle orders from this user. And the developer writing this code, because that's what you could do, is just wrote a log statement. Like, log info, creating user, first name, last name. Innocent, right? And now suddenly, well, this, like, your front end was the thing you patched. The front end was the thing that, oh, this is a web server, this is exposed to the internet, I'm going to have to keep that up to date. The billing system in the back, not so much. It's running a 2-year-old Java version, and maybe its operating system hasn't been patched in a while, because it's like firewalled 5 times. Nothing could possibly go wrong. And now this simple exploit that travels in strings now has made its way to some insecure system in the back, and well, it gets logged there, and suddenly we've got arbitrary code execution and some internal billing system which hasn't been patched in 2 years. like I'm kind of like being very archetypal in my description here, but like this is stuff that actually happens in practice. Like these random servers in the back are very often a thing that exists, because like system administrators also have like schedules. Nobody wants to patch the 15th server on the left if they don't have to. I mean, they should, but like very often the intrusion vector for attacks is the 15th server to the left. Everybody kind of knew you should keep up to date, but everybody had been going like, I will do it next week. We'll do it next week. And then it never happens. So, because of how easily this attack propagates, like this just gets stored in a string and just gets forwarded somewhere as a string, and then just runs again and again and again. Eventually, you're going to again hit a system that hasn't been patched because everybody forgot it exists. And then you've got arbitrary code execution again, which is bad. So yeah, this is a flaw that we're going to be hearing about for quite a while. Like we heard about it in December because it was in the news, but like in the business, so to speak, this is going to keep cropping up. Like we're going to keep seeing new systems get compromised by this vulnerability. Well, simple because everybody has to patch their log4j and on every server ever, and that's not going to happen for quite a while. So yeah, that is log4shell. That is the vulnerability that broke the internet at the start of December, or mid-December, I think, was when it really kicked off. Yeah, the fix, of course, is disabling this GNDNI thing for substitution, and I think they just disabled everything that wasn't Java, like environment things, like Java properties or whatever. Essentially they limited the protocol thing, the JDNI, where just JDNI, they limited the protocol to a whitelist, which is just Java, I think. That's the fix. So yeah, that is log4shell. That is how Minecraft broke the internet. Moving on. Second thing that was requested is VPNs. You wanted to know how virtual private networks work. So look, new magical from December. In the first lecture, we talked about the network again, and we said we're going to do computer organization and networks, but everybody is evil. And the takeaway we arrived at is that the lower level layers are really good at delivering data. If everybody plays nice, then they're good at delivering data reliably and quickly, but they kind of suck if anybody is malicious. They're not really built to handle that kind of thing. Yeah, takeaways: you cannot trust that you're talking to the right person, you cannot trust that your data is confidential, you cannot trust if your data is unaltered, and these things have to be taken care of by the application layer. So yeah, the internet is a scary place. That's how you could summarize that. When you send data, it bounces between some unknown number of, or unspecified number of unknown routers. It travels between a bunch of devices somewhere on the internet. We don't even know which ones. We don't know who owns them, who controls them, who are we talking to. Before you at some point get a reply from somewhere and you don't know who sent that reply, but they're claiming to be the person that you're asking for. Anybody along the way could be up to no good. Anybody along the way could falsify this reply, intercept this reply, block this reply, modify this reply. Anything with no safeguards. This is a terrible idea. What if the application layer, the one thing that we're trusting to take care of these things, doesn't? That would be bad, right? Like, what if one application along the way, any one, you have, like, how many applications are on your computer right now, running, talking to the internet? What if one of them isn't taking care of these things? Well, you're screwed. Not necessarily, but it's a problem, is what I'm trying to get at. So, people thought, well, we could fix that. We want to fix that. So what is the idea behind a VPN? That's what we're getting at. So the idea is that, I do not trust the network layer. I do not trust the Ethernet layer. What was it called? Data link layer. I don't trust the data link layer. I don't trust any of that. I want security for everybody. So let's look at our internet. So I gave these two devices random IP addresses. And let's look at what the idea is. So the idea is we establish at the application layer an encrypted authenticated tunnel. So the stuff we always have been doing. Now, I'm not going to go into details of how the cryptography works here. One, because there's like 20 different VPN protocols out there, and each of them does it slightly differently. And two, because it's essentially the same stuff that we've been already talking about in this lecture. You do some sort of handshake between the two sides, using some sort of cryptography to assure each other that you are in fact the person that you're claiming to be, and then you establish some sort of shared secret that acts as an encryption key. And then once you have done this handshake, you can then use the symmetric encryption key, possibly with additional key derivation along the way, whenever you feel like it, to then communicate data securely. Same stuff as SSL, same stuff as SSH, same stuff as all the various crypto protocols we've talked about in this lecture. The exact details vary. So you have this secure tunnel, which I have drawn in green, using my mouse. That's why it looks weird. We have the secure tunnel. What is step 2? Step 2 is we slap addresses on each end. So now we take this application layer connection and we just pretend that this application layer connection is a real network card. That is what we do. So we tell the operating system, hello operating system, I am a new network card driver that has just been, I'm a new network card driver and I've just had a cable plugged in. There is now a new connection available. And this connection now has an IP address. In this case, I picked random ones in private address space. We now have a new connection. And what is the next step? Well, we reconfigure the routing table. So we change the routing table. You will remember the routing table is the thing that your device uses at the network layer to figure out which way to send data, which way is the internet, so to speak. We reconfigure the routing table so that instead of using your normal internet connection, you're now using this new pretend network card to send data. Yeah, and that's the idea. So we just change the default gateway to be the other side of this tunnel, this made up network card, and then our network card driver just takes any data it's supposed to send, encrypts it, sends it over the tunnel, and done. That's VPNs. That's the entire thought process. Like we pretend that our secure tunnel, we pretend that our application layer connection is a network card. That way we can tell the operating system, make every connection using this network card, this pretend network card. And then all this network card's driver does is, well, all that. Like what this network card's driver does is it takes any data it's supposed to send, encrypts the data, ships it off across the secure tunnel, authenticated to the other side, and all done, right? I mean, easy. Internet solved. We don't need nothing insecure anymore. Wait, I mean, obviously not. Like, I mean, you are up to my tricks at this point. You know, I'm not everything is actually solved. So yeah, we've securely managed to get our traffic from Alice's computer to this VPN server over there. Hooray! Now what? Well, now the question is, where are we actually trying to go? Like, where is this traffic supposed to be going? Scenario 1, traffic goes somewhere on the internet. This is the scenario that might be the one you are familiar with. Like, if you're using a VPN to, let's just say, make private use backup copies of popular movies, then you're probably connecting to a random server on the internet somewhere. By the way, don't do that. It's a bad idea. You're using a VPN to connect to a random server somewhere on the internet. Well, what happens to your connection? You go through this secure tunnel in green to the VPN server. And then what does the VPN server do? The VPN server makes an makes a regular TCP connection over the internet to your target in red. And your target is somewhere on the internet. Yeah, but like, isn't this just the same problem? Like, you end up with the same problem, right? You end up with the same problem of all of the internet-based shenanigans that we've talked about in this lecture that we were trying to solve are still possible. Like, they're not possible against you, because you are, well, on your side, the tunnel is secure to your VPN server, but from the VPN server to the target, well, not really. I mean, you're still vulnerable to DNS hijacking, you're still vulnerable to any kind of routing attack. Yeah, quick list, you're protected against what? You're protected against local attacks. Like this, I'm not trying to say this is useless. Don't get me wrong, this is a useful technology. You're protected against local attacks. So if you're in a coffee shop and Eve is pretending to be the access point, or if Eve is an attacker that is just hijacking just sniffing packets on the Wi-Fi, you're protected against that. So if you make an HTTP connection over this tunnel, then Eve cannot read your cookies, even though the connection itself is unencrypted, because it goes over this encrypted VPN tunnel, because it's going over this pretend network card instead of your real network card. You're protected against local attacks. Many local attacks, at least. You're also protected against, obviously, logging from your ISP, because your ISP, the only thing that your ISP sees is that you're connecting to the VPN server. Your ISP cannot see where the connection goes after that. That's good. What are you not protected against? Any internet-based attacks? So anything that, like any kind of like routing attacks, any kind of like DNS hijacking, compromise of DNS resolvers, compromise of DNS servers. Any of the shenanigans you can get up at that level, obviously, well, I mean, you are protected, but your VPN isn't. So like you're still, like the connection from the VPN to the target is still unprotected, unless the application layer takes care to be secure. But if the application layer takes care, obviously, then, well, what are you worried about? Yeah, bulk data inspection. Yeah, if Agent Smith is recording your data at the back end, then Agent Smith is still recording your data at the back end, just with a different source address. Obviously, like it's still traveling from the VPN server to the destination over the internet. What are you slightly impeding? Saying very slightly, figuring out the connection source. Where is the connection coming from? Because obviously the source IP address is not going to be your IP address, but the source IP address is going to be your VPN's. I say slightly because people keep logs. Even VPNs that claim pinky promise, we're not keeping any logs. Let's just say don't exactly have a stellar track record when it comes to not coughing up logs the moment law enforcement comes knocking. So yeah, like your VPN might be telling you pinky promise, I'm not gonna log, but then when the police shows up with a warrant, they often find out that, oh no, actually we did have logs all this time, and here they are, by the way. So yeah, slightly impeding that, because somebody can just come knocking on your VPN's door. What's the scenario 2? This is the one that people care about on the business level usually. Well, okay, that's not entirely true. People also care about scenario 1 on the business level. Like, you are concerned that an attacker might be compromising your, like, for example, websites. Like, you are concerned that an attacker might compromise a website by just sitting in a Wi-Fi and hijacking an HTTP connection. Like, that is a concern even in a business environment. But the thing that only makes sense in a business environment is scenario 2, where the traffic that you're sending doesn't actually go back on the internet. Instead of going back on the internet to some destination, your VPN server is in the same local network or network environment as your target. So for example, if I'm at home, working from home, and I am dialing into the Institute's VPN, and then connecting to some internal file server at the Institute. That's the scenario. My connection goes from my home to the Institute via this VPN tunnel, encrypted, secured, and then once my connection gets there, everything travels through the internal networks of the Institute. It doesn't ever leave to your grats. So we are reasonably sure that at that point there is no attacker in the network anymore. Or if there is, we probably have a problem. So yeah, that is scenario 2. The traffic stays internal to the target, which does actually protect you against all the internet-based stuff. So it protects you against any form of internet-based traffic interception or monitoring, assuming that your cryptography at the VPN level is good, which is what we're assuming here. It protects you against routing-based shenanigans, any of those stuff that we talked about where you can hijack a connection on the internet and pretend you're the target. That doesn't work anymore because everything is going over the VPN, and this requires strong encryption. You are obviously not protected against denial of service attacks. Like any attacker that can stop your packets from being delivered can just stop your encrypted packets from being delivered. You are immune against targeted denial of service. Like for example, if the attacker is only trying to stop connections to certain websites. You are protected against that because the attacker cannot know which packets on the connection belong to which website. So the attacker can either kill the entire VPN connection, or the attacker can just not do anything. But the attacker cannot go, oh, I'm just going to stop you from accessing this website. You're also not protected against metadata monitoring. I'm going to talk about that in a second. So yeah, that is VPNs. That is the idea behind a VPN. We just make an application layer connection to a target server using strong cryptography authentication, exchange shared secrets as usual, and then we use a pretend network card driver to tell the operating system, oh, this is a new connection and you should use it. And then this network card driver just takes any packets it's supposed to send, encrypts them at the application layer, sends them off across the tunnel, the internet, across the secure connection, within this encryption layer, authentication layer that we established, sends it off to the target unpacks it into the side and just does network routing stuff on it. That's a VPN, that's the idea. And we had a point, metadata monitoring, and we are going to jump straight into that because that's our next point for the lecture. Actually, are we going to jump straight into that? Yes, I think we are going to jump straight into that, and then we're going to go on break. So, going straight into privacy and metadata. What is metadata? So I just used this term, and you hear this term used a lot. If you're working in privacy circles, you're going to hear the term metadata a lot. But I figured it would be useful to have a look at what it means. So metadata, meta being a Greek prefix, means data about other data. So it's data that describes other data. That's not very useful. Let's look at an example. So Alice and Bob are communicating. And Alice says to Bob, tomorrow at 4, same as usual. Okay, so what is the data that Eve might be trying to intercept here? The data is the content of the message. The data is tomorrow at 4, same as usual. So the data is, oh, Bob and Alice meet tomorrow at 4. Or potentially the data could also be Bob and Alice often meet at 4, because it's the same as usual. Like, this is data. This is the content of the transmission. What is metadata? All of these things. The first bit, Alice talked to Bob. Like, that's data about the message. It's not the content of the message, it's the recipient of the message. That's metadata. Alice talked to Bob. Second bit, Alice sent a short message to Bob for some definition of short. So, for example, was it a one-line text, or was it a 5-paragraph or 10-page essay? Or Alice talks to Bob every day at 9 p.m. Patterns, right? Like behavioral patterns, timing, right? Alice called Bob, five minutes after this bank robbery was committed, Alice called Bob. Random example, right? But that's metadata. That's data about data. It's data about the connection, about the message, but it's not the content of the message. And you can see how this is a problem. right? Because none of the cryptography that we have covered in this lecture does much about this. Like, the traditional encryption modes aren't gonna, like, I mean, just don't even attempt to obfuscate who's talking to whom. Like, you're just taking a message, you're doing cryptography stuff on it, you arrive at a ciphertext, and then you say, well, transmit the ciphertext and decrypt it. Well, transmit the ciphertext. You're still transmitting a message. It's just like the data is garbled, like the content is inaccessible to Eve, but the fact that you're sending a message is accessible. The fact, okay, when are you sending a message? Accessible. How long is the message? I mean, there's like some padding concerns, like you're probably going to apply some padding to your ciphertext to pad it to a certain multiple of the block size or whatever, but within like some margin of error, usually, yeah, accessible. Like you can distinguish between 5, like, how many bytes is that? Like 64 bytes of data or 5 megabytes of data. Like you can distinguish between those two things, right? Just because by how much data is being sent. So yeah, this is a problem, right? So yeah, why does it matter? I have some motivational examples for you. First one, yeah, undercover journalist phones home. Yeah, you probably don't want to like have it be noticed that you're communicating to a foreign journalist organization if you're in the kind of country where you need to go undercover as a journalist. And another one for the more capitalism-minded of you. A company's R&D division suddenly starts talking to their patent lawyers. Like the company it's known that the company is researching some groundbreaking new technology in the field. And for a long time there's a lot of like nothing, a lot of silence. And then suddenly the R&D division starts exchanging emails with the patent office every day. You could deduce, even without knowing the data, even without knowing the content of the emails, you could deduce that there's probably been a breakthrough. Otherwise they wouldn't be talking to the patent lawyers. Yeah, the third one hits a bit closer to home, I suppose. Yeah, teenager suddenly starts browsing Planned Parenthood's homepage, being an abortion organization. Fourth one, informant sends a message to police investigators. Yeah, probably also very good not to have it known that you're communicating to the police if you're an informant. Or a teenager in Iran starts researching their identity. Yeah, like if some of these hit too close to home for you, or if some of these make you uncomfortable to think about, that's a good thing. This is a bit of a wake-up call. The technology that you and I are building impacts real lives. Like, this isn't all fun and games and, oh, Alice talks to Bob. Sometimes these are life and death situations. You could ruin, well, your bad security, your bad cryptography, if misused, could actually ruin lives. We don't like to think about it, but that's a reality of our job. Yeah. The message being, often disclosing association by itself is dangerous. Not the fact that what you are saying could be disclosed, but that you're saying something to a certain person could be dangerous to you. Like the simple fact that you're communicating to somebody could be dangerous. Okay, well, didn't we just have a solution for that? We just talked about VPNs, right? Why don't we just solve our problem by talking to a proxy server? Or a VPN server, I suppose. I mean, it's the same concept. So Alice talks to this proxy server and says, oh yes, please talk to Bob and send message M to Bob. And we assume that message M has some sort of encryption on it so that it's authenticated to Bob. So Bob knows it's actually from Alice. So we do not have concerns about man-in-the-middle attacks here. We're assuming that this message is properly authenticated. And then the proxy goes and sends this message M to Bob, and Bob can just authenticate that it's from Alice. And this solves our problem, right? I mean, it doesn't, because otherwise I wouldn't be asking this question, but it seems like that, right? It seems like, oh, problem solved. What do our interlocutors on the internet see? What does our ISP see? Well, we see that Alice is connecting to the proxy server, but we cannot tell whether Alice is talking to Bob, or Alice is talking to Charlie, or Alice is talking to anybody on the internet. What was the problem? Well, the same as before. I mean, we already touched on this a little bit. So Alice talked to the proxy server, and then the proxy server talked to Bob, and the proxy server now knows that Alice talked to Bob, right? Because the proxy server got a request from Alice that said, please send this message to Bob. And the proxy server knows that Alice talked to Bob. So the proxy server, proxy server, I changed this mid-slides. The proxy server obviously knows all of Alice's browsing history, right? I mean, that's the problem here. But surely I'm gonna cut to the chase. It says on the slides, but surely they won't tell anyone. Of course they will tell somebody, that's the point. Yeah, obviously we have talked about this in the first lecture. The power of law enforcement is scary indeed. Yeah, somebody can just show up on the proxy provider's doorstep and go, yeah, pursuant to whatever act of whatever, either you give us all of the access logs pertaining to Alice, or we're gonna sue your ass. So yeah, faced with criminal charges, it turns out that many VPN and proxy providers are suddenly discovering logs that they were very sure they didn't keep. Yeah. That's a problem. Like, recall back to the slides where we had motivating examples. At least in some of these examples, I mean, I can flip back to it. At least in some of these examples, your attacker, your adversary, is the kind of entity that would have that kind of access. Like the fifth bullet or the first bullet. Yeah, these are attackers that have that kind of access to force, let's say, a VPN provider in Iran to disclose access logs. Like, they have the legal authority to do that. So yeah, that's a problem. If you have data, you can lose data. That is kind of the message that I'm trying to convey here. If you have data, you can be forced to disclose it. You can accidentally disclose it, either because, well, it's very easy to have your servers compromised, as previously established throughout this lecture. You could also be keeping the data even though you don't know you're keeping the data. Logging is a big one, and not in the context of log vulnerabilities, but in the simple context of lots of servers just do logging by default. For example, let's say you're setting up a web server to handle some API for your communications app. Like, you're designing some secure communications app, and you're setting up a web server to handle your API, and you just, well, your app code is perfect. Your application code is perfect. Your application code does not store information about who's communicating to whom. It's perfect. No data is being stored. Great. Yeah, the problem is, of course, that you're using a web server, and, well, maybe you just installed, I don't know, Apache HTTP server, and by default that server does logging, which means you have a few gigabytes of log files containing metadata of your users that maybe you weren't even aware you had. Right? Logging can be unintentional, because many frameworks, many servers do logging by default. Many firewalls do logging by default. So you secure your servers with a firewall, makes sense. Your firewall is logging connection information about all your connections to do DDoS protection. Well, now you have metadata that you didn't know you had, which you can't be sued over, or sued for, I suppose, or could leak if your servers are compromised. Yeah, keeping data 100% safe if you have it is impossible. I didn't say hard, I said impossible for a reason. Because, again, if I say keeping data safe is hard, people are going to take that as a challenge. People are going to go, oh, I'm better than these fools. I'm a professional software developer. I am not going to make any mistakes, and I'm going to keep my data safe. As I think I have sufficiently covered in this lecture, no, you're not. No, you won't. Be realistic. The better solution, of course, is don't have the data. That's the fix. If you never get the data, you can't lose the data. let's talk about how that works in practice. So what I'm going to plug here is the Tor project, illustrated on the right. So we again have on the right our Alice and Bob setup, except they look different this time because I reused this picture from a different slide set. So they look different. They're computers now instead of people. So Alice is talking to Bob. And before we had this setup where we had a single proxy server along the way. And then Alice talks to the proxy server and tells the proxy server, okay, proxy server, please send a message to Bob. And then the proxy server obviously knows that Alice talked to Bob. Now, what is the idea behind the Tor project? It's the idea that, well, this one proxy server knows who Alice is talking to, but we just add more proxy servers. That is the very, 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 very fundamental idea. So we have, in this scenario, a bunch of different proxy servers, obviously more than 9, like obviously a very much larger set than 9 of possible proxy servers. And now Alice picks 3 at quote-unquote random out of the set to use as proxy servers, and then goes, well, okay, first proxy server, we're calling it Charlie. Charlie, please talk to Frank. Send this encrypted message. And then the encrypted message, encrypted to Frank, so only Frank can decrypt it, says, okay, please talk to Georgia and send this encrypted message. And then this message is again encrypted so that only Georgia can read it. And then Georgia's message says, oh yeah, please talk to Bob. And then Georgia talks to Bob, and then we do the entire dance backwards, and the data arrives at Alice's computer. That is the very, very, very fundamental idea behind the Tor project. So each jump, each hop along the connection can only see its direct neighbors. So Charlie knows that Alice talked to somebody. Frank knows that somebody, like, there's a connection coming from Charlie and there's a connection going to Georgia, but doesn't know who it's from or where it's to. So Frank is just sitting in the middle so that Charlie and Georgia don't know each other. And then Georgia is there and knows, oh, there's a connection coming from somewhere and it's going to Bob. But nobody in this picture actually knows the entire route except Alice. Not even Bob. Like, Bob only sees Georgia. Like, Bob only sees the exit node. Alice knows the entire connection, of course. But none of the proxy servers actually have this dangerous information. That's the beautiful thing here. Like, even if you have your servers logging everything by accident, even if law enforcement hijacks your server and goes, you must now log everything, you can't. Like, you can't log information that by design you don't have. That's the beauty of it. Nobody sees the entire route. Yeah, and we know, like, I'm not just saying, like, oh, this is secure, like, this is this great cryptographic concept, and somewhere in some shady back room there's a bunch of people in suits and black glasses laughing at our foolishness that we think that this is secure. No, we actually know that as of 2013, which, okay, is 8 years ago at this point, but it's the most recent information we've got, at least as of 2013, our government attackers actually weren't able to compromise the Tor network. We know that because of, as part of Edward Snowden's file leaks, that one of them was an internal presentation at some agency or another that essentially talked about the Tor project and how it's seeing more and more use and how, well, their efforts to compromise it have been met with very limited success. So, yeah, we actually know that the stuff is secure, at least 8 years ago. I mean, like, we don't know if it's still secure, obviously, but as of 8 years ago, this concept worked, with some very limited exceptions. Traffic in the Tor network is very hard to de-anonymize, because you would need all 3 nodes in this graph to communicate, to collaborate. Like, you would need Charlie and Frank and Georgia to all be in cahoots with each other, to all be communicating and sharing data, so that they can together de-anonymize Alice's connection to Bob and figure out that it's Alice connecting to Bob. Otherwise, nobody in this graph actually knows everything, and no two actors in the graph can cooperate either. It would have to be all 3. Which is very unlikely. Because of the very high number of Tor nodes, it's very unlikely that 3 of them are controlled by the same government entity. Obviously, there is some traffic analysis you can do. There are some technical shenanigans you can get up to that involve tricking the user's computer into giving up the identity. Any sort of application layer attacks, like for example, sending you a file download for a PDF that's actually an executable, or sending you a docx document that actually runs macros. Anything like that, obviously, well, it completely bypasses all of this. Like, if the target server, Bob, can send you files. And if you're accepting a file from Bob, and it's actually from Bob, like, you are cryptographically ensured that it's from Bob, but if you accept this file and you open it and it compromises your computer, then the Tor network obviously can't help you. But at the network level, this is pretty much as good as it gets. Now the obvious trade-offs, this is slow. It's gotten better, but like compared to normal internet speeds, the Tor network is very slow. But it's good that it exists, and it does have a measurable impact in important scenarios. Good. So that is that. Yeah, recap for data storage, a few lessons for you to take away from all of this, since we haven't really talked much about stuff you personally as a developer can do. Don't store what you don't need. That's maybe the biggest lesson. You don't need to store every little bit of data. And that is something that is antithetical to a lot of the folk wisdom that makes the rounds, especially in application developer circles, where a lot of the time people say, oh, just store it. Storage is cheap, right? Storage is cheap. You don't know if you're ever going to need this data. Like maybe 5 years down the road, you want to add some feature that makes recommendations to users based on their past behavior. And then, well, suddenly, because you had the foresight of logging all of your users' data all the time, well, you have this giant data set that you can now make use of. Imagine if you didn't have this. You couldn't roll out your recommendation feature. Well, yeah, but like the point that's being dismissed here is, of course, that, well, if you log all of your user interactions all the time, yes, you have a large data set, but also, yes, you have a large data set. Like, you don't just have data that is useful, you also have data that you need to protect. And as previously discussed, you have data that you very well might not be able to protect. Either because Eve compromised your computer, because there was a vulnerability in a logging framework that you were using that you didn't know about, that nobody knew about at the time, you couldn't have patched because there wasn't a patch yet, and you just got compromised, and suddenly all of your user data is gone. Oops. Or because law enforcement shows up at your doorstep and goes, yep, here's a warrant, please give us all the data. And that it's very difficult to say no at that point, by which I mean impossible. So, yeah. The second point, of course, is think about what is data. So far we've always talked about data, we've always talked about message contents. Think about the fact that information about the message, metadata, is also data. Is also stuff that might be dangerous to somebody if disclosed. Is also stuff that at the very least on the principled level is private, and that you shouldn't disclose. You should, if possible, not even gather or even not even have available to you. The not having available to you part is maybe a bit difficult for you as 5th semester students, because, well, you don't have the cryptographic background to develop your own cryptographic protocols, nor should you. But at least at the storage level, you should try not to store data that you don't need, and that includes metadata. So, for example, if you're delivering messages to somebody, well, consider not storing the message after it's been delivered. Like, I know this is a very popular thing in web development cycles. When somebody clicks delete message, very, 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 very many services are just going to say, okay, update the database to set the deleted flag to 1. And then just don't show the message anymore because it says deleted, but it's still in your database. Like, you don't want to, you don't want the risk of, like, there's a risk that you're gonna leak this message 2 years down the road because somebody hacked your user database and suddenly they have access to every single message your users ever sent, including the ones they deleted. Like, that's a problem. That's like a problem that very often gets overlooked. It's like, if the data is there, then you could lose it. I keep going in circles, I suppose, but like, don't store it if you don't need it. It's that simple. Think about it when you're developing, when you're designing. And of course there is a trade-off there. Like, for example, a user clicks delete on their post. Well, maybe 5 minutes later there's going to be a support ticket saying, oh, please, I clicked delete by accident. Can I get my post back? And then you do probably maybe consider wanting help desk to be able to go, oh yes, sorry user, I clicked the restore button, it should be back now. Like, that is a fair consideration. Like, there is a trade-off there. But that is a trade-off. You need to realize that this is a trade-off. If you keep storing it, then there is a security trade-off. Do you maybe want to store the post for 48 hours so that you can restore it? Yeah, makes sense. Like, that's fair. You can say, okay, somebody deleted a message. I'm going to store it for the next 48 hours in case that a support request comes in that, oh, I deleted this by accident. That's good. Do you want to store the message forever? Because storage is cheap anyway, like maybe we're going to need it at some point. No, you don't. Like, that's the core message here. You don't want to store it forever. Maybe store it for 2 days, 3 days, a week maybe, like short time frame. And then afterwards, goodbye. Get rid of it. Delete it from the database. You don't need it anymore. Make sure it's gone. Like, the less data you have, the less data you can lose. Is a straightforward message here. Yeah, trust is good. Protocol level security is better. If you never get the data, then you can't lose it. Simple idea. If you want to know more about metadata avoidance or any of the stuff that we've talked about so far in this course, you will want to attend master's level information security courses, where a lot of the stuff is going to be covered in more detail and with more cryptography attached. Because a lot of the stuff that we've talked about so far is only a little insight into the stuff that's out there. One point, by the way, bit of a personal point since I'm a personal proponent of this, but what's the best protocol level security? Not using a server sounds dumb, but consider how many of your applications actually need a smart web server. Many don't in the modern internet. Like, there are many, many, many things these days that you can just do entirely in the client. Like, if your application, for example, like this is an application I wrote, is your application accepts some proprietary file format and then extracts data from it. Like, you have some proprietary software that writes output files, and these output files are just some custom-made XML. And you provide a web application that lets users read this input file, and well, they get like human readable output. Essentially, it extracts data from this arbitrary file format. Now, the normal, I want to say naive way of, or like naive sounds a bit insulting. The traditional way of doing this would be, well, you just have like a form and you just submit the file to the server, and then the server does some processing, and then you get the file back and you get your output. But if you think about it, this is a data security nightmare. Like, you are getting some unspecified user file in some proprietary file format, which might have any amount of personally identifiable information in there, and you are accepting this as a file upload, which means it gets stored in some arbitrary temporary directory owned by your web server on your disk somewhere. You don't even know where. This file gets saved there, and then hopefully at some point the operating system deletes this temporary directory. Maybe it doesn't. This sounds bad, right? Like, you have a file and you now need to take care of how to safely store this file that you're trying to process. How do you avoid this conundrum? Very easily, by doing all the processing in the browser. like, there is no rule saying that your browser cannot do file processing. Like, JavaScript is very much capable of doing XML parsing, for example. So instead of like sending the file to your server, doing the processing on your server, sending the file back, as is the traditional model, in the modern day and age, you can very much just read the file on the client device, process the file in JavaScript on the client device, and then display the output on the client device. You don't need a server involved. This is both secure, like more secure in terms of data security, because, well, if your server never gets the file, your server also cannot leak the file, obviously. And more secure, it's more efficient. Like, think of the scalability. Like, in a traditional model, maybe your server can handle 5,000 file operations per hour, but what if you suddenly grow to 20,000 users? Like, your server is going to be overloaded. You're going to need a new server. If you do your operations on the client device, well, that's infinitely scalable. Like, if you have 20,000 users, you also have 20,000 client devices running your stuff. Like, at this point, all you're worried about is serving some static files, and like content delivery networks are great at serving static files. So, yeah, that's I suppose a point on the data storage thing. Do more stuff in JavaScript, please. Like, if you don't need to involve a server, don't involve a server. Like, you don't need it. You can just do a lot of your operations in JavaScript and never have to touch a server. Just static files. Send the files. It's very hard to compromise as well. Static HTTP servers are pretty hard to compromise. If you're not processing user data, it's very hard to be compromised because you processed user data incorrectly. Like if an attacker uploads a malicious XML file to your service, then suddenly you need to worry about, oh, how is my XML parser on the server going to react when it sees some entity inclusion tag that tries to load the etc password file? If your XML file is being processed in the client, like the same client that is selecting the file, then, well, I mean, what's Eve gonna do? Do an XML inclusion attack on Eve's computer? Sounds pointless. So yeah, you can't really be compromised if you don't touch the user data, because the user data is being processed in the user's browser. Yeah, that's also the upside. So do that. More processing in JavaScript, please. Anyway, I'm going a bit off topic here, I suppose. The next chapter is going to be the network analysis toolchain. Stuff that you might be using if you're doing network stuff. This is the bit that everybody's been waiting for. This is the bit where I show you the cool tools that you can use to do all of this stuff in practice. But before we dive into that chapter, we're going on break. It is now 10:45 on my clock, and we are going to reconvene at 10:55, so that's in 10 minutes time. We're going to reconvene, and we're going to dive into the network analysis toolchain, and then we're going to wrap up the networking part of the lecture. So I will see you all in 10 minutes, or for those of you on the YouTube VOD, I'm going to see you in roughly 10 seconds once you get off the couch and click 10 minutes forward. Bye-bye until then. Works better if you unmute the microphone. Alright, it is 10:55. Welcome back to information security. Or, well, for those of you on the YouTube recording, welcome back from 30 seconds ago. So we are going to talk about the network analysis toolchain, or, well, as much of it as I can fit inside a 30-minute part of a lecture. So before we do that, though, the presenter works better if you turn it on. If it's actually turned on, this should work. Yeah, excellent. So, we've got an old friend that's dropping by for some wisdom. Mr. Parker here, or at least Mr. Parker's uncle, would have you know, with great power comes great responsibility. By which I mean, I'm about to show you some actual tools that people actually use in practice to do actual network security stuff. These tools can be used for malicious purposes. You should not use these tools for malicious purposes. No, not even because it's funny. No, not even because you want to try them. Like, these are real grown-up tools for doing things. Please use them as such. Yeah. Generally speaking, you want to use these tools on systems that you control. If you're just practicing, right, you can do this stuff to your own server. Nobody's gonna care. You should not take these tools and point them at random other people. No, not even your brother, who I'm sure is gonna think it's hilarious. Don't do it. No, don't. Stop. Don't do it. Not even Google. Yes, I'm sure Google servers are fine and you're not going to break them until you do. And until somebody comes knocking at your ISP's door going, oh, your customers are attacking our servers. Don't do it. Either because you're worried about the repercussions, or because, like, on a basic human interaction level, it's a bad thing to do. Like, we live in a society and we should maybe act like it. So yeah, these tools can do real harm to real computers. Please don't misuse them. Yeah? You can, like, if you have consent from a company that you're supposed to test their security, go ahead. But generally speaking, like, don't point these things at random people. Like, treat it like a gun. Don't point a gun at random people. Okay, with that out of the way, let's jump in. So the first one is one you've probably seen in previous lectures. First one is Wireshark. This is one of the more old and venerable network analysis tools. Essentially what Wireshark does is it takes a log of every single packet that your computer sees. So it just captures every single network packet that your computer reaches your computer, including ones that are not meant for you. So you will recall that we talked about Wi-Fi and it being a shared medium where everybody can see everything, pretty much. Yeah, so if you're in a Wi-Fi network, like I'm here, like this is a Wi-Fi network. This is a Wi-Fi network that I set up for testing, containing devices that I control. Yeah, so you see where I'm going with this? Don't try this on your home network. At least not if, like, other people are connected to it. So yeah, and you can see that this just has a log of every single connection, every single packet being sent on a connection. It does. It supports very, very, very many different protocols. So, for example, here we have an HTTP request that is being made for an OCSP check. So this is a request to the certificate authority for Teograts Online that is requesting information about whether the certificate is still valid. And you can see that Wireshark actually breaks down this Ethernet frame into these components. So it goes, so this is an Ethernet frame, this is an Ethernet 2 frame being sent from this network card to this network card, Contained in the Ethernet 2 frame is an IPv4 frame, which is sent from this IP address to this destination. Contained within this IPv4 packet is a TCP segment, which is being sent from a source port random to a destination port 80. The sequence number is 430, the length is 430 bytes, the acknowledgement number is whatever. And then contained within this TCP fragment is an HTTP request, post request to this host with this data. So all of the stuff that we've been talking about in theory so far, Wireshark breaks it down for you. Of course, the problem is that, well, the problem is twofold. The first part of the problem, of course, is cryptography. More and more applications use cryptography, thankfully, which is good, but it also makes Wireshark less useful. Like 15 years ago, when I was in middle school, you could fire up Wireshark and on any public network, and I mean, you shouldn't do that, but also I was in middle school. You could fire up Wireshark on any public network and find any number of Facebook login tokens flying in plain text over the ether. And just hijack them. Like there were browser extensions for this stuff. Like there were Firefox browser extensions that would just fire up Wireshark and capture session tokens, and you could just click the account and log in. It was very amusing, in a sense. But also you shouldn't do it. In the modern day and age, of course, most connections are going to use HTTPS. I had to go out of my way to find something in Wireshark that actually had human readable output. Because like you can see that it captured 5,000 packets almost, going from my computer to some server on the internet. Most of those are encrypted to some degree. So most of those are HTTPS or at least some sort of garbled ciphertext that I cannot read. I ended up finding this OCSP request which is made in HTTP. But of course the response itself uses encryption to make sure it's genuine. But the request is readable, so yeah, I found a thing that I could show. But Wireshark is getting less and less useful by the day because, well, at least at the application layer, most applications use encryption, which is good. Yeah, captures and records all data visible to your network card. It does automated filtering. Like you can, for example, see at the top, I'm filtering for HTTP. So I can only see HTTP packets. It allows for manual inspection of data, so you can just in the UI inspect the packets. And it also allows exporting into a variety of machine-readable formats. I'm assuming that at least some of your practical exercises had to do with that. So you would get a packet capture from Wireshark and would need to parse that packet capture for something. Yeah, you can export to any kind of format, JSON, HTML, text file, XML, C byte arrays, I believe. Any number of formats. Now the second problem, remember I said two problems. The second problem is it only captures packets that are visible to your network card. And as you might recall, Ethernet in the modern day and age is a switched medium. Meaning, yeah, this is a recap from Con. Ethernet switches understand link layer data. They can read the source and destination MAC address of your Ethernet frame. They will record source addresses to build a mapping between address and switch port. And then they are only going to send packets to the appropriate port for the destination MAC address, minimizing the wasted bandwidth and reducing collisions. Which, of course, raises a problem because in a switched network, as opposed to Wi-Fi, which is why I use Wi-Fi for the example, in a switched network, wired network, our computer is only going to see the packets that our computer is meant to receive, as opposed to the packets being sent from a neighboring computer to the gateway. But also recall from December when we talked about the data link layer being very bad at authentication, by which I mean not doing it. So we had this example of an attack called an ARP spoofing attack, where Eve misleads the parties of IP traffic
into thinking that Eve's MAC address is associated with the other party. So here we have Alice communicating with the default gateway, and Alice asks on ARP broadcast, okay, who owns the IP address of the default gateway, and then Eve wins a race condition and goes, yep, that's me. I'm the default gateway, here's my MAC address. And then Alice sends the IP packet to the default gateway by specifying Eve's MAC address, at which point the switch obviously routes it to Eve. And does the same thing to the default gateway, and then just forwards the messages. So Eve just inserts a listener in the middle and intercepts all traffic without it being noticeable by anybody. This is a software that does that. So this is where you get to do this in practice. It's called EtherCap, and it's a suit designed for man-in-the-middle attacks. Any number of man-in-the-middle attacks. ARP spoofing is one example, but there's a number of them. Let's go through them real quick. MAC flooding, that's the other network attack we discussed on layer 2 in the first lecture. The one where you knock out a switch's SAT table by just spamming different MAC addresses, and once it runs out of memory, it purges legitimate entries and starts just flooding output to everybody. Can do that too. DHCP spoofing, that's one we didn't discuss, but you can probably see where this is going. DHCP, the Dynamic Host Configuration Protocol, is a protocol that your computer uses to get an IP address. So when you plug your computer into a network, then your computer asks on the network, hello, is there any DHCP server available that wants to give me an IP address? Because I don't know what IP address I'm supposed to be using. And DHCP spoofing attacks this because, again, there is no authentication. So Eve just tries to win a race condition against the genuine DHCP server and just give the same reply as a genuine DHCP server. So you give a genuine IP address, but instead of the genuine default gateway, you give Eve's IP address, so that the traffic gets forwarded from the victim to Eve and then from Eve to the internet and nobody notices. Yeah, that's DHCP spoofing. Physical network interception is a bit more, well, literal. Like, so far we've always talked about interception in the data sense, in the, oh, we're doing something digitally on the network. Physical network interception is literally, you cut the cable and you insert yourself in the middle. That is physical network interception. So you literally like infiltrate a data center, unplug the cable from the switch, plug it into your network interface, and then plug a second cable from your network interface into the switch. So you're literally inserting your laptop in the connection. And then what your laptop does is it just takes the raw data on one wire, forwards the same raw wire out the other data, making it perfectly transparent. Like, there is no like data artifacts of this because it's just your computer forwarding it one-to-one. It looks the same as a regular wire to everybody involved, except obviously you're intercepting all the data on the wire and can do shenanigans. Also a bunch of data stream manipulation features. You can inject reset packets. That's a really popular and brute force technology for denial of service. You're going to recall that the TCP protocol does connection management between two hosts over the internet and has no authentication by itself. So authentication happens at the application layer. So your application layer software, your browser, establishes a TCP connection to the target, and then using this TCP connection on this unsecure medium, transmits a request for authentication. So starts an SSL handshake. What reset injection does is it just injects a garbage packet into the stream that has a reset flag set, which is essentially the flag that the other side would set if it tried to close the connection. So essentially it's just injecting a closed connection packet into the connection, and because it's not authenticated at the TCP level, well, the other side just has to trust it. So For example, if somebody wants to prevent you from connecting to a certain web server, remember the VPN examples? If somebody's trying to prevent you from connecting to, or even if somebody is trying to prevent you from connecting to a VPN, it's also a possibility, they can just inject these reset packets and just cut the connection. Like that's something you can never prevent even with a VPN. Unless you're using UDP, I suppose. Then you can work around that. So yeah, reset injection, really popular even in the real world. China does this, for example. The Great Firewall works in many ways by deep packet inspection, so looking into what the packets are doing instead of just the target address. And then if the packets look suspicious, so for example, the content of chat messages is suspicious, or the protocol being used is suspicious, for example, if it looks like it's a VPN, then the firewall just injects one of these reset packets and forces the connection to be dropped. Very, very brute force and very, very effective. Ettercap can do that once you have intercepted a connection. Also arbitrary packet injection, of course. If you're if you're a man in the middle, if you're controlling the connection, you can of course just inject arbitrary data. Keep in mind, of course, that if the application layer software is encrypted, if it's using encryption and authentication for its connection and using it properly, well, you can't inject data without being noticed. That's the point. But for insecure protocols like HTTP, you can inject arbitrary content. Fun. Yeah, and any other number of shenanigans that you can get up to if you're a man in the middle. Also, a variety of passive monitoring features, similar to Wireshark's. A lot of these tools have some overlap at some point. Yeah, this also does some passive monitoring, similar to what Wireshark does, so just sit in the network and listen. Alright, next bit of software. This is an old one. I used this when I was in middle school. I shouldn't have, but I did. AirCrackNG. AirCrackNG started out as a tool for breaking web networks. Remember, the web standard wired equivalent privacy was one of the Wi-Fi standards that we discussed. And we discussed it extremely briefly, by which I mean we gave it a red X and just said the cryptography is broken, don't use it. You can use WPA. Yeah. So the cryptography is broken to the degree that you can break it within a few minutes on a home laptop. And AirCrackNG, the original thing it did was exactly that. It cracked Wi-Fi networks. That's why it's called AirCrack. So originally it used to be used for breaking Wi-Fi. Then over time it grew into Wi-Fi attack suite. It does real-time key recovery. For example, if you are using WPA2, it can do the dictionary attacks that we talked about in the lecture, where you capture handshakes and then apply a rainbow table to figure out the password, if it's a common password and SSID combination. It can forge packets if you have a key from arbitrary hosts. It can retroactively decrypt. That's another thing we discussed in the Wi-Fi part, where we said, and there's no perfect forward secrecy, so if you capture the encrypted data stream, and at any point in the future you find out the password, then you can now retroactively go back and just look at all the data, which is what forward secrecy is supposed to prevent. And yeah, it can do that. So you can just Wireshark capture or any other software capture data stream over a long period of time. And then once you finally figure out what the Wi-Fi password is, you can go back and look at all the conversations. It can do many, many more things. It can do reset injection, like we discussed in the Wi-Fi section, where you disconnect somebody from Wi-Fi and force them to reconnect. And yeah, many, many things. All right, Nmap. That's a really old one, and really also one of these venerable old networking tools. Nmap is a port scanner. So what Nmap does is it connects to a target server, and it tries to figure out what ports of the target server are accepting connections. So yeah, server scanning and reconnaissance. You're attacking, you're pen testing a company. So you have permission to attack their servers, try to find vulnerabilities. So what do you do to start out? Well, you just figure out what is running on their servers. And Nmap does that. Nmap just tries to connect to every port on the server and sees what happens. And then it does a lot of smart logic in the background, because operating systems behave differently for different port states, simply because of how the kernel is written. So for example, here you can see it can figure out that the firewall is filtering 2 ports, simply because the firewall rejecting a connection looks different than the server rejecting the connection. Because the server's operating system reacts differently to a rejected connection than the firewall does. So Nmap can figure this out. Nmap can figure out that port 22 is open, and it even tries to establish a connection on port 22 and figures out SSH key sizes supported. So it figures out that these 4 keys are offered, and presumably that means that the server accepts these 4 algorithms. So we can, for example, easily have a look and say, oh yes, this is a known insecure SSH algorithm, I can now break into the server. Port 80 is open, it even does an HTTP request and goes, oh yeah, let's look at interesting stuff. We're looking at the title that we're being sent, and we're looking at the server header, which if it's being offered, tells us what server is supposedly running on the other side. I mean, we have to trust it, like the other side can send whatever it wants. But by default, all the web servers send genuine headers. So in this case, the server claims to be an Apache web server 2.4.7 running on Ubuntu. The same happens for SSH, by the way. It also does SSH version detection. You can see it's OpenSSH 661p1, again running on Ubuntu. This is useful because, well, what if you have some exploit or some vulnerability that only works on unpatched HTTP servers, for example? So you have a vulnerability that only works on Apache 2.3, and it was patched in 2.4. Then you can now look at this and go, assuming this isn't lying, which, well, why would it be? This vulnerability is right out because this is a 2.4 Apache. Meanwhile, if you have some vulnerability that was patched in 2.5, well, you could try it. Yeah, 135, 139 are both filtered. Makes sense. Those are like Microsoft remote desktop and file sharing. Makes sense that a firewall wouldn't allow those. 9929 and 31337 are open. Yeah, that's random services. It also does OS detection. So Nmap can figure out what operating system your target is running based on how different operating systems respond to connections. So, for example, we talked about this in computer organizational networks. So you might not have heard it, but window sizes in TCP dictate how much data the other side is supposed to send, and is determined by each side. So if I connect to a server, the server is going to reply to my connection request, telling me, yes, acknowledging connection, like connection established. Also, you're allowed to send up to 20 kilobytes of data before I have to reply again. So the server sends me a window size saying you're allowed to send 20 kilobytes of data, and then I'm not allowed to send any more data until the server tells me I'm good to go. And what it's doing here, for example, is different operating systems have different heuristics for determining window size. So a Linux kernel might or likely react differently to a connection request by advertising a different window size than a Solaris kernel or a Windows kernel or a Mac OS kernel. So all of these operating systems, while they implement the same protocol, have detectable differences in how they choose certain values. Nmap can use this to figure out what operating system you're running. So in this case, it's Linux. Well, yeah, we kind of figured because the server header says so, and the version detection for OpenSSH says so, but still good to know. Yeah. Many different scanning techniques. Yeah, SynScan is the normal one. You just try to connect and see what happens. TCP ACK scan is for figuring out if there's a firewall. Because an ACK is invalid but should produce a result from the target if the port is closed. At least in most operating systems, if you send an ACK packet on a closed port, you're going to get a reset from the target, so connection rejection. And if you send it to an open port, you're going to get no response because it's invalid, it just gets dropped. So the ACK scan lets you figure out if there is a firewall blocking it, because or if the port is actually closed. Because if there's no firewall, then a closed port is going to produce a reset. Yeah, it uses OS peculiarities, just differences in implementation to figure out what operating system you're running, and or if the port is open, closed, filtered, or whatever. Yeah, the goal being determine reachable ports, figure out what services are running on the target, so you can then proceed to attack those services. What if you do not like the command line? Because command lines are awkward and finicky, and you need to remember like 15 different switches, and you need to figure out what -a means, and nobody wants that. Well, I have a UI for you. This is one of the most popular tools out there, called Metasploit. It's an exploitation framework. It encompasses many of the features that we've seen so far in the more hobbyist tools. The problem, of course, is that it's a professional tool, meaning money. There is a free version which has reduced functionality. It encompasses most of the functionality we've already seen in terms of scanning for hosts, or at least the features we saw in Nmap of scanning hosts for exploitation, identifying the services. And then also the thing about it is that it automatically, like in an extensible framework, allows plugins to be written for vulnerabilities. Meaning that you have automated plugins that can scan your target server for these vulnerabilities based on its version. So for example, if you scan a target and the target uses a 3-year-old OpenSSL version on its SSH port, and Metasploit detects this, then Metasploit can also tell you, oh, and there are 5 known remote code execution exploits for this host. Do you want me to try them? And then you can tell Metasploit, yes, please run these remote code execution hosts, and if you succeed, run this payload which spawns a reverse shell, for example. So you can like select the payload you want it to run, all in the UI. You can select your pre-constructed reverse shell payload, and then you select the plugin for the exploit, and then you just say run. Exploitation made easy. Now what is dear Spidey here rappelling in to tell us? Do not randomly push buttons in Metasploit. Like, so far I've kind of been doing it as a wink wink nudge nudge thing. Don't do this. Don't do this. Like, the tools we've talked about so far are pretty benign. Like, Wireshark is just passively scanning the network, right? Like okay, EtherCap is a bit intrusive, but still, like, it still doesn't try to break the network. Unless you're, like, physically cutting cables, don't do that. But, like, it still doesn't damage the network, per se. And Nmap is pretty benign. Like, most applications are not going to crash on an Nmap scan. Metasploit can and will crash servers. Like, if you just randomly let this go on a random server, or any random embedded device, you're going to break it. Like, there's a very real chance that the server is going to crash, there's going to be downtime, and it's your fault. Like, the person running that server is probably not going to care that, oh, I heard about this cool framework in information security and I wanted to try it on your server. Like, this is a chainsaw. Don't point the chainsaw at people. Okay? Especially like embedded devices. Like, you can totally target your home printer using Metasploit. And your Metasploit is maybe going to tell you, oh, there's like 15 possible exploits for this home printer. And then you're gonna push try all, and then suddenly your printer starts sputtering and doesn't turn on anymore because you broke it. Like, this is stuff that can actually brick devices if you misuse it. Don't randomly push buttons unless you know what you're doing. Okay? Yeah, the next one. What if you want a all-in-one package? This is more professional stuff because professionals don't like having to mess around in the command line all the time. They like buttons. Kali Linux is a Linux distribution that is focused on penetration testing. So this is a live Linux distribution. You can just boot from a USB drive or a CD. And it comes with hundreds of pre-installed tools, including all the stuff we've talked about so far and many, many more that are used for pen testing. It comes with a bunch of technologies for remaining undetected in a network. For example, with the click of a button, Kali Linux can pretend to be Windows. So you click like one button and suddenly your desktop looks like a Windows desktop, and all your applications look like Windows applications. Really cool and good for being undetected because well, nobody's gonna ask questions if you're using Windows 10 in their lobby, but if you're booting scary looking black command lines with green text in your lobby, then maybe people are gonna ask questions. Yeah, it's live bootable, so you don't even need to install it. You can just boot it straight from a USB drive. Very useful. Same as before. Very useful, very good at doing things if you know what you're doing. If you don't know what you're doing, you can brick devices. Like, you can brick a device by targeting it with wrong exploits. You shouldn't be able to, but especially for embedded devices or older servers, you can definitely kill them or, yeah, like permanently damage them, especially for embedded devices, which often aren't designed to reboot cleanly. Like, if you nuke some random configuration file into an unusable state on an embedded device, there's a very real chance that the embedded device just doesn't turn on anymore because it tries to load the configuration and fails, and then it just reboots again. Then it tries to load the configuration and fails, and it just reboots again. And then it tries to load the configuration and fails, and well, you need to buy a new printer because you pressed random buttons. So yeah, don't randomly do things unless you know what you're doing, please. Like, at least research what the tools do and like get an idea of what they're doing before you let them loose on random devices, even ones you control. Like I said, try to figure out how the chainsaw works before you turn it on, please. And yeah, that is the last of the tools that I'm going to talk about today. It's the all-in-one package for penetration testing. And with that, we're at the end of the lecture. Let's do some user interaction. So for the last 4 lectures, we have talked about computer security. And we have talked about how secure or insecure our devices are. And now I want to get a quick bit of audience reaction. After hearing this lecture, how do you feel about computer security? Like, do you think we're in a great spot? We've got this under wraps, or are we all doomed? Is the internet a great mistake and we should probably just turn all the computers worldwide off and never speak of this again? Okay, there's like 4 people awake. The rest of you have fallen asleep. So yeah, we're all doomed. 2 votes. Only Sheffield and Absolutes, 3 votes. Yeah, that's true. I needed to give you a 3rd option, otherwise it felt unfair to ask this question. I promise it's not that bad. Like, I realized that for the last 4 lectures, I've harped on about everything is broken and everything is bad and there's so many flaws everywhere. And the funny thing is, somehow it still works. Somehow the internet still exists. Somehow there aren't constantly data breaches everywhere. I mean, there are data breaches, but not all the time. Somehow we manage to not constantly lose data, misplace data, have data be compromised. That's not saying that there isn't a lot of that going on, but like, it's all still working somehow. So like, it's not all doom and gloom. The internet exists, functions. It's just a matter of, well, we have to keep one step ahead of the other side, and we need to keep improving it. like many of the decisions of the early internet age, in retrospect, seem a bit gullible. Like, they were a product of their time, when every actor in the network was more or less accountable. When the internet was still a loose collection of universities, research organizations, where, well, every actor was to some degree accountable. Like, if you ended up with a computer from University of Michigan doing bad things to your server, then your countermeasure was calling the IT admin at the University of Michigan and going, one of your students on this computer is doing bad things. And then the computer administrator at U of Michigan would go into a classroom, find that student, and dress them down. And that would solve the problem. Now, the problem with the modern internet, of course, is that we have lost that accountability to a large extent. Which is good. Like, we spent today's lecture talking about metadata avoidance, which to some extent is, we don't call it that, but it is avoiding accountability to some extent. Like, we are making a choice here to value anonymity, privacy, but we are accepting at the same time that this also makes it easier for bad actors to stay anonymous, to stay private, to not be identified. Like, that is a choice that we're making here implicitly. And in light of that, in light of this decision that we collectively have made, which you may or may not agree with, that we value privacy and we value users being non-identifiable. In light of that, we also need to reevaluate computers. We need to reconsider many of the technologies of old in this context of, well, we no longer can call the IT administrator at U of Michigan and tell them to yell at the student that is doing bad things, because we don't know where the attack is coming from, and we kind of need to deal with that. But it's not all doom, it's not all gloom. The internet is still working. And of course, there is a selection bias here. I mean, in this lecture, we are going to talk about the things that break. We are less, at least in my part, less going to talk about the things that don't break. I assume that at least in Maria's part, you were being told about technology that works instead of only being told about technology that has broken. So yeah, that is the first bit. The second bit is a bit of immediate feedback. So there's going to be a proper feedback form from the university later, of course, about the course, where you can give us all the feedback you want about what we did. But now that I'm concluding my lecture, I also want to poll you for like immediate stuff that comes to mind. Because like I know that in 2 weeks time or 3 weeks time, whenever you fill out the feedback form, you're not going to remember everything. Well, now that we just spent 2 hours going over at least 1/4 of my content, I figured that some of you might have some feedback that they wanted to give on the lecture. So yeah, that's what this slide is for. And if nobody says anything, then I'm just going to stand here awkwardly for 30 seconds, and then I'm going to flip to the next slide. As you do. Yeah, that's the end of the 30 seconds. Oh, great lecture. Yes, exactly. Thank you. I like hearing that feedback. Like the motivation, of course, behind getting feedback is that, well, I mean, this is not going to be the last time, probably. Like, unless I did horribly and Maria is going to court-martial me, this is probably not going to see the... this is probably not going to be the last time I do this lecture. Like, I'm going to do this lecture again. I should flip to the first slide. There we go. Now you can actually see the responses. So this is probably not going to be the last time I do this lecture. I'm kind of expecting to do it again next year. And of course, I want to always improve the experience I give to the students. Even in this difficult environment that we're in thanks to the pandemic, I try to make it as useful and applicable to students as possible. But I am, as a PhD student, somewhat removed from the experience of you folks that are like in a 5th semester. So like I rely on feedback, any kind of feedback, like unstructured or highly structured, to figure out what works, what doesn't work, what I want to change for next year. When I revise these slides for next year, figure out what went well, what didn't go well, like what could have been explained more clearly, what wasn't obvious from the lecture, what was obvious from the lecture, what was done well, what wasn't done well. Yeah, that's why we need feedback. Like, we rely on you giving us feedback to be able to improve the lecture for next year. So like the feedback you give us directly improves the experience for everyone that takes this course in the future. All right, that is the end. That is the end of information security from my side, or at least the end of introduction to information security from my side. Of course, if you want to hear more about information security, you can. Well, I mean, there's gonna be a Q&A session next week, of course. Stay tuned for that. There's gonna be some form of outro lecture session next week. We're gonna figure out the format and get back to you on that. And then, of course, there are more information security lectures in your future, if you'd like. There is an entire master's catalog dedicated to information security with lots of lectures, just like this one, or hopefully like this one. Yeah, you can sit in on that. Even if it's not not one of the catalogs that you're attending, you can still at least listen to some of our lectures. As you might have noticed, the last four lectures, I am very much of the opinion that every developer should have some background in information security, simply because information security is everywhere. In everything you do, there are information security implications, and if you don't consider them, then you might be doing real harm to real people, and what seems trivial to you might not seem trivial to others. Keep in mind, what started as a silly school project of a teenager in a garage that was trying to chat up his friends at college ended up as a global phenomenon with billions of users that is responsible partially for genocides. Our decisions in software design, while you might not be the next Mark Zuckerberg, our decisions in software design have ramifications beyond what we might imagine, and it's important to think about that and deal with that reality to some degree. Alright, on that slightly grim note, thank you for listening. Thank you for joining me virtually for the 4th time in a row as I speak into an empty void in my room. There's going to be a lecture next week. There's going to be a lecture exam at some point. You'll get details on that. That will be in person, so I'll see some of you through our masked faces there. And yeah, that is information security. Thanks for listening. Stay healthy. Get some rest during the holidays. And eventually, we're going to get through this and we're going to get to have in-person lectures again. Thanks, guys, and have a nice day.